Hello. We will put our skills in machine learning into practice in this exercise. In this exercise, the job is to create a machine learning model to automate a decision-making process that used to be conducted by a human expert or a human decision maker in the organization. This particular class of application is popular. Today, many people make important decisions in organizations, and granted, these people are important and are human experts. On the other hand, many often these people become very busy or overloaded, and very often the organization risks the turnover of these important decision makers. So there are two ways of automating the decision-making process of a human expert. One way is to go and interview the expert and try to get at the mental process and the steps that they use to make the decisions. And then once we do that, we can automate the process by writing a program to mimic the decision making of that person. This approach may work depending on the application and also the person. Some decision-making situations involve very clear input and very clear outcomes. In this situation, it could be useful to talk to the person to get to their mental process of making the decision. An example for could be approving a loan application. There could be some guidance, some factors that the loan officer looks at before approving the loan, such as the candidate credit score, and maybe they have some range of, cutoff points they use to inform their decisions. In other applications, this process is very hard because the input and outcomes are not very clear. So think about medical diagnosis, for example. So yes, there is a patient and there are a couple of factors that a doctor or a medical practitioner looks at, but it's much more ambiguous and fuzzy than a loan officer looking at a loan application. Here, machine learning is very useful because machine learning makes use of historical data. We don't need to have the person to talk to or interview with, although that may be very useful. We can look at historical records, uh, past decisions made, and we can learn a model that mimics the decision-making process of that person. In this particular application, we have an employee in the organization who works in the purchasing department, and the employee's job is to receive requisitions from staff to buy a product or service and decide whether to send it for technical approval or not. So if you take a look at the data frame, which is loaded from the CSV file, the first column in the data frame is the decision outcome, whether tech approval is required or not. 0 means no and 1 means yes. In addition, we have the requester ID, the person who requested this purchase, the role of that requester in the organization, which can be either technical or not technical, and the product itself, the quantity, the price, and the total. All right. So in this data set, first, if we are going to build a machine learning application, and in this case, it's going to be a supervised machine learning application, we need to figure out what are the predictor features and what's the target feature. So let's take a look at the data frame. Remember from our discussion of machine learning that the target feature is what we're trying to predict. In this case, it's very clear that we're trying to predict tech approval required. On the other hand, what are some of the predictors that may be useful for making that prediction? So at first sight, we may say, okay, everything else here may be a predictor. But if you look at these predictors, not all of them are useful. For example, requester ID, it could be useful in the sense that maybe the employee has a certain tendency to approve requests from a certain person or deny requests from another person. But that's usually not a very good feature to use, because even if that was the case, it's kind of indicative of some bias toward or against a certain person. So we should be very careful, and when we use historical data, not to kind of imprint biases in this data into our machine learning model. So we're going to exclude requester ID. If you take a look at the rest of the features, role, tech or non-tech, product, quantity, price, and total, it seems that total here is purely redundant because total is the quantity times the price. So it may be not very harmful to add it into a model, but it's not very useful, and most likely the model is not going to include both quantity, price, and total because total is purely redundant in this sense. Okay, so we have decided that um, the target feature is tech approve required, and the predictor features are role, product, quantity, price. Now let's take a look at these data in more detail. And a very first step when we have a data to feed it into a machine learning model is to check the data types of the columns in this data frame. Now here, obviously, you can see that requester ID, role, and product are all object because they're a string, which is a problem for many and probably most machine learning models because they expect numerical features. So we need to convert role and product. We shouldn't worry much about requester ID into numerical features. So the way to do it, and there are two ways, is either to map each value of each category to a certain number, or to create dummy variables, another variable for each value. Each of these approaches has pros and cons. If you have a variable which only takes two values, two category, then it's probably a good idea to use the first approach. We can give 1 and 0 for the two categories, respectively. If we have a variable that takes many categories, so let's say like 10 or more, assigning a value for each category is not the best way to go about converting it to numerical, because this assignment will be ad hoc. So if, let's say, you've got three categories, apples, oranges, and bananas, for example, then you can do 1 for apples, 2 for oranges, and 3 for bananas. But if you do so, like, you have induced an inherent ordering in your data that basically says apples are less than oranges, oranges are less than bananas, right? So that's not the best way to go about that when you have multiple categories. So first, what I'm going to do here, I'm going to look at how many categories I have in both role and product. So if you look at data role here, you see that you've got tech and non-tech. So maybe we've got tech and non-tech, but we don't really know in between what we've got in here. So one way to look at those two binary categories is either to convert it to a set. So we can do set data role, and here we see for sure non-tech and tech. So set will just keep kind of track of the unique values. Or we can use the function value counts from our series, which actually will count the values. So you'll get the unique values on the index. So we've got mostly non-tech and some tech. Request by tech and non-tech. So let's do the same for product. I'm going to use the set here, set data product. And here we've got a bunch of products here. So what I'm going to do, I'm going to convert data role to a binary. And since non-tech and tech are the two categories, I'm going to give 0 for non-tech and 1 for tech. That makes it consistent with the notation used in this data. And I'm going to create dummy variables for data product here. So what I'm going to do for data role is to write a function, and this function is going to take a role as a parameter, and then I'm going to apply this function on the series. So I'm going to create a function, let's call it convert role. This function is going to take that role as a parameter, and if this role is non-tech, I'm going to return a 0, otherwise it's going to return 1. Okay, so this function takes a single value, but I want this function to operate on the whole series data role. So what I'm going to do, I'm going to use the function apply. So the function apply, if you remember, basically takes a function and applies it on the whole series, basically mapping each element in the series to 0 or 1. So in this case, I'm going to apply this function convert role on data role, and that's going to give us a series of 1s and 0s. What I'm going to do with this series, I'm going to store it in the data frame, and I'm going to create a new column. Let's call this column data tech role instead of role, so we make sure that tech role means 1 if it's technical and 0 if it's not. Okay, the next step we need to do is to convert product to numerical variable or variables in this case. I'm going to use the second approach, which is to create dummy variables. Remember the concept of a dummy variable? It's basically a variable of 1 or 0 depending on whether the category is a certain category. So a dummy variable for desk, let's call it product desk, is going to be 1 here and 0 here. 0, 0, and 1. Now you need to create as many dummy variables as you have categories in your categorical variable here. So it kind of becomes a bit tedious because you need to do this for like 5 or 10. Thankfully, Pandas comes with this function called getDummies, which does exactly the same. Mapping each one of the categories into a dummy variable. Now, if you run pd.getDummies on the data, you're going to notice that it's actually created a dummy variable for all categorical variables, including requester ID, including role. So we've got role, non-tech, and role tech, and including the products. Which is not what we want because we only want the product. So before feeding data into pd.getDummies, what I'm going to do, I'm going actually to drop the variables, the columns that we no longer need. So I'm gonna drop requester ID, I'm going to drop role because we don't need it anymore, and I'm going to drop total as well. So we can either fancy index our data frame or use the function drop. As the name implies, it drops columns or rows. Actually, it drops either columns or rows based on their indices. I'm going to drop column in this case. So I need to tell drop that the axis here is columns, because by default it drops across the row axis. And I need to drop requester ID, role, and total as well. So you can see that we've got ourselves a new data frame here. It doesn't change the original data frame, which is fine. I don't want to kind of change the original data frame. I can keep it, just in case. And I can assign this to another data frame if I wish, data2. Or if I want to override the data frame, if I don't need it anymore, I can just assign it to data back again. Now the last step is to get the dummies. And you notice here that we've got dummies for product only because that was the only categorical variable here. So we've got a dummy variable. Instead of having the product being either chair or cleaning or desk, we've got a bunch of dummy variables. So I'm gonna again override data. And here I've got the data set, which is now ready to be fed to the machine learning model. The very last step we need to do is to extract the target feature and the predictor features from this data set. So in this case, the target feature is obviously data tech approval required. So that's my Y, that's what I am trying to predict. And the X is everything else. So I can either fancy index my data frame, or because I've got many columns here, instead of fancy indexing, I'm going actually to use the same approach here to drop. I'm going to do X is equal to data.drop, and I'm going to drop tech approval required. Let's not forget that the axis should be columns or 1, because otherwise it's going to try to drop on the row axis and we're going to get an error. Okay, so let's take a look at the X, right? Everything but tech approval required. Let's take a look at the Y, and that's tech approval required. Okay, so now that we have those separated, the next step is to split our data into a training dataset and a testing dataset. And this is really important because if you train your model on the whole data, there's a danger of overfitting the data, and this results in a model that, although results in a good performance, it may not generalize to future data points. So what we're going to do, we're going to use the function train test split. And this function takes our X and Y, and also takes the parameter of the training size. In this case, I'm going to go for 0.75. Now, every time you run this function, you're gonna get a different split because there is an element of randomization in this function, which is fine if you're doing this model and you want to deploy it and you don't want to repeat or look at the process of creating it many times. But very often we would like to be our model to be reproducible, in the sense that if I run this notebook, no matter when I run it, I'm going to get the same result. If that's what you want to do, you can pass another optional variable called random state. And random state basically initializes that random number generator. If you initialize it with the same random state, you're going to get the same split. So with that here, I'm going to, this function returns 4 things: xtrain, xtest, ytrain, and ytest. Looks like we've got an error here, so ytrain and ytest, a comma here, okay. So we've got that taken care of. And now we can go ahead and create the model. So it's a supervised machine learning model, and the question here, is it a classification or a regression problem? And the answer ultimately depends on what you've got here in your Y. And in the Y, I've got categories, 0 or 1. So this is a classification problem, and I'm better served with a classifier. There are many classifiers offered by scikit-learn package. We're going to look at the decision tree classifier. So that classifier will train decision trees. And decision trees are useful because they're very interpretable, so we can take a look at the tree and also interpret it and use it to inform our understanding of the decision-making process. So the first step is to create the tree, and I'm going to go with the default hyperparameters here. The next step is to call the function fit and pass in xtrain and ytrain. So again, I am training my tree on the training data set. So now I've got my tree. Before just looking at the tree, I need to make sure it did a good job. So I'm going to test it. So the way to test it is to have it classify observations that it hasn't seen. So I'm going to look at yFit, and I'm going to call it yFit test, and I'm going to call the function predict on X test. So again, don't forget that the tree hasn't seen X test, it has seen X train. So I'm testing it on X test, and I'm asking it to classify observations based on the this data set that it hasn't seen. Let's fix the typo here, predict. Next, I'm going to test, and I'm going to use two metrics. One of them is just one number, which is accuracy score. So accuracy score, y test, that's the true observations, right? It will take y true and y predicted. And y predicted in my case here is y fit test. In this case, you notice that we've got 1 or 100% accuracy. It means the tree managed to classify all observation in both categories correctly, which is really impressive, and there is no need to do any more benchmarking, but for the sake of completeness, I'm going to use print the confusion matrix. So again, same idea, true and predicted. And the confusion matrix is going to show the performance across the two categories. So in the first category, which is 0, non-tech, approval none required, we've got 207 observation correctly classified as the same category, and the other category we've got 43 observations. So obviously we don't have any confusion here because the accuracy is 100%. All right, so we have trained a machine learning model, and that model can be now deployed to make decisions on new purchase requests. Before we kind of end, we're going just to try to interpret the data. Interpret the model, because interpreting the model is useful for understanding what the model picked up from the data. So what I'm going to do, I'm going to use the function export tree to the tree, decision tree. And this function will take the tree and will take the feature names. So the feature names are going to basically be the columns on the feature matrix. And I'm going to print the tree representation, which will show in text in here. So let's try to read through and understand what's going on. So first, let's take a look at the first split, product desktop computer. If it's less than 0.5, which means it's 0, it's going to test whether it's a laptop. So first, it's testing whether a desktop. If it's not a desktop, it's going to test whether if it's a laptop, same. If it's not a laptop, the class is going to be 0, meaning tech approval none required. Required is 0, right? So it means the tech approval is not required in this case. However, if the product is a laptop, it's going to look at the tech role of the requester. If the tech role is 0, less than 0.5, it means the role is non-tech. Tech approval required is going to be 1, right? So approval will be required. However, if the requester is of a tech role more than 0.5 means 1, then technical approval required is going to be 0. Okay, so that's for a laptop. Let's continue here with the split here. So if it's not a desktop, it means here it's a desktop. So if the product is a desktop, if tech role is less than 0.5, it means that's a non-tech role, then approval is going to be required. Otherwise, approval will not be required. So that's very interesting, because given all of those features to the tree, it seems that the only thing that mattered for the tree to make a decision here is to look at two things. Two categories, desktop and laptop, and the tech role of the person. So basically, we're approving any non-computer purchases by default, but any computer purchases are only are automatically approved without technical approval if the person requesting them is a technical person. Otherwise, they go to technical approval process. So that's really interesting, and that's kind of a gets to the decision-making process of that person. It's a good idea if the decision maker is available to try to consult with them. Does this tree make sense? Is this their mental model? Can they reflect upon it? But basically that's the model, and it's ready for deployment, and we can use the model to automate the decision-making process. So next time somebody requests a purchase, this purchase can go to the machine learning model, or the machine learning model can be used to help the decision maker filter through the request and make quicker and more efficient decisions. So that concludes this exercise. I hope this exercise illustrates both the process and the value of training, testing, and deploying machine learning models.